Hello, my name is Pedro Morales. I'm a teaching professor at the Math Department at University of California, Santa Cruz, and this is Math Talk. During this first week of classes, we touched very important ideas in Precalculus and Linear Algebra. But before we go into that, let me just share a reflection about multitasking. I think that we have exposure to multitasking in this remote setting, and we have to be very careful about it. There's a lot of research done in the so-called multitasking deception, because even though we feel that maybe we can do a lot of things at the same time, the reality is that we don't perform as well as just sticking with one task at one time. So we have to be careful whenever tempted of grabbing our phones to check something while in class, or maybe switching tabs during a meeting in Zoom. We have to be very careful because in the end, we are just deceiving ourselves into thinking that we can do a lot of things at the same time, but actually our performance is way below. So I think this is an important thing to keep in mind while transitioning into this remote setting. Now, let me just share with you a couple of important ideas starting with precalculus, because this week we talked about three important things. We talked about functions, how to transform functions, and one of the most important applications of modeling, which is linear models. The main idea in mathematics in this case is that one of a function. And a function, think about it as a way to relate two or more variables. In precalculus, we try to focus only the relationship between two variables. But for example, later on, like in linear algebra, you will relate more than just two variables, maybe 3, maybe 17. So the idea of relating variables is fundamental for mathematics and for modeling. We have different ways to describe functions, and we talked about 4 different ways. We talked about graphs, tables, description with words, and equations. And really depending on the applications and what you are specifically doing, each of these descriptions will be more suited for your particular application. It's important to keep in mind that we can transition from all of them. Then we also talked about transformations. One of the most fundamental ideas in mathematics is that we want to generalize properties. We don't want to create a long list of things that we need to memorize, but actually the opposite. We want to simplify everything that we're trying to study. And transformations help us to simplify the way we can describe functions. Instead of describing all of, say, quadratic functions, maybe I can just understand very well a couple of quadratic functions and then transform those in order to create all the possible solutions that I have. So transformations are fundamental for understanding the generic case. And we have 2 main types of transformations. We have horizontal transformations and vertical transformations. These will behave in very similar ways, although in the end we have that horizontal transformations. We have to be careful about them because whenever we want to add, they actually end up doing the opposite of what we would expect. Same thing happens with scaling. And that brings me to an important point. We have 2 types of fundamental transformations. We have shifts and we have scaling transformations. So in the end, we can classify transformations in 4 different types. We have horizontal and vertical, and each of them can be shifts or scaling. So that's an important thing to keep in mind. And then finally, we talked about linear models. Now, linear models are one of the most important models in mathematics because as human beings, we tend to think about linear models in a more natural way. For a lot of applications, we usually tend to think about linear models as the first option. From physics to engineering, to science and sociology, everything that we try to model, we always start with a linear model. That's really the main reason why we want to really understand what's going on with this type of models. And that actually brings me to the idea of linear algebra. So linear algebra is a generalization of dealing with linear models, and that's basically what we saw in this first week of classes. We saw that instead of grabbing just a linear equation with 2 variables, we can generalize this with multiple variables and actually multiple equations. And we end up with a system of equations. So a system of equations is nothing more than the generalization of that precalculus idea of relating two variables with a very particular type of equation. Once we have a system of equations, we want to find solutions for that system of equations, and we can do this by following something that is called an echelon form for that system of equations. Now, this is a very formal way of solving a system of equations, and it's very important for us to understand this because this provides us with a very particular algorithm that we can follow no matter what kind of numbers we have. So writing down a system of equations in echelon form makes our lives easier and actually can help us to code a program that will solve a system of equations. That's one of the main applications. Then we talked about how we can introduce matrix notation into solving system of equations. And the idea of using matrices is that later on we will see that we can treat matrices as numbers. That means we can multiply them, we can add them, even we can kind of like divide them, which in the end we will figure out that that is multiplication by an inverse. But the important thing is that we can treat matrices as a generalization of numbers. So if we can translate the information of a system of equations into matrices, we actually have the tools of algebra to work with it. The idea of rewriting a system of equations into a matrix also basically brings us the idea of writing down an echelon form of a system of equations in a matrix way. And that's how we arrive to echelon forms for matrices. Basically, the idea is the same, although we do have certain differences between what we understand as an echelon form for a system of equations and an echelon form for a matrix. That's super important to keep in mind. And finally, we were thinking about reduced echelon forms as a very specific way of solving systems of equations. So this brings us with a very precise method to solve system of equations using matrices. Another very important idea that we talked about was the idea of a vector and how to combine vectors together. And this combination of vectors is what we usually call a span of a vector sequence. That is, if I have a sequence of vectors, I can compute the span, which is the set of possible linear combinations of these vectors. This is very important because that will generate something that we later will call as a vector space. So a vector space, we can think about it as the set of all possible linear combinations coming from an original set of vectors, a sequence of vectors. Now, these ideas are going to evolve during the whole quarter. Hopefully, these are making a little bit more sense now. And little by little, we're going to gain deeper understanding in what we're doing. So thanks for watching. Thanks for being here. And I'll wait for you next week for more insight in this math talk.